Again to our fifth installment now of our AP Physics 1 review series. We are just 10 days away from the AP test. So we're over halfway through our series and we're starting to get down to that crunch time here. We've only got 3 chapters left, including this one, and then our last one will just be a review of everything here. Before we get started, I am gonna really quickly check the audio levels on the stream just to make sure we don't have any weird audio artifacts that are the bane of my existence. Here we go. Okay, I can hear myself. Does it sound fairly clear? Fairly clear. All right, we're gonna call that good enough. And that being said, let's get going. We're gonna kind of move like we did last time, where we're going to start by going over some of the concepts that we will see in this unit kind of broadly. We're going to go over them generally and see where these equations come from and how they might be used, and then we'll do some practice, start again with multiple choice, and then move on to a couple FRQs. So that being said, let's take a look here. So when we define momentum, we usually think of it as a mass times a velocity. We often express this with the variable p. And so this means this is a quantity that is intrinsic to moving objects. And so if our velocity is 0 in our reference frame, then we consider the momentum to go to 0. And if the mass goes to 0, for our circumstances, we will consider the momentum to go to 0 also. It is possible to have momentum without mass, because light has momentum, but light does not have mass. However, this takes much more complicated mathematics to explain clearly here. So for our purposes, we're only going to be using momentum as mass times velocity. And so we have to be a little bit careful here, though, because if we have multiple sources of momentum in our system that we're accounting for, we have to add them together linearly. So this might look something like an m1 times that's velocity, so we'd call that a v1, plus then some second mass traveling at its own velocity, v2. Now bear in mind, we have to then set up what our coordinate system would be, and so if these are moving in opposite directions, one of these velocities has to pick up a negative sign. And so one of the main staples that we're going to be working around with is we expect momentum to be conserved inside of our system, which basically just means very similar to what we saw last week with our energy. We expect our final momentum to equal our initial momentum. And this is for all the energy in the system. So this could be the momentum of like 2 blocks colliding. We have to sum up both of their momenta like this. Or it could just be a single block. Or maybe we'll deal with collisions where the blocks will come together and then move as one singular mass. And we'll see what that looks like in context. But we do have to work out, so this is for a closed system. We do have to worry about cases where we have outside forces from outside of our system affecting our momentum. In order to account for this, we have to include a term for an impulse. And so our impulse term, we add, like we added our work term to energy, that's just going to be a plus j. Now this j, we can quantify. Typically, we will write this as a force times time. This is the average magnitude of the force times the amount of time this force is being applied. So we see some similarities between work, but we want to make sure that this is going to be a little bit more intuitive, so we want to show where this kind of comes from here. And so to do that, we're actually going to jump back down to its relation in the conservation equation here. And so let's take this equation, but unpack it a little bit here. We're going to assume we have a mass moving at some some velocity that then has an outside force that changes its velocity. So our final momentum will be our mass m traveling at some v final. And we can compare that to our initial momentum, which is the same mass, but traveling at some v initial. We don't need to really worry too much about how these relate to each other, just as much as we know that v final is after the change from the force. This can either be to accelerate it, to increase our velocity, or to decelerate it, which is technically another form of acceleration, just in the opposite direction, which reduces our velocity. And then we can plug in our definition we had for J, which would be our force times time. So what we can do is we can bring this term over here, giving us mvf minus mvi is equal to f times t. And we can go ahead and see that on the left here, we're multiplying by the same mass in both terms, so we can actually factor that out. And that would look something like this, pulling the m out, and then we can write a quantity, or a set of values inside of a parentheses, times for our vf minus vi. So if we were to distribute this through using distributive property, we would be able to get back the same thing we had on the line above. And this is still equal to f times t. And then if we divide by t, we get m times, we'll have vf minus vi over t. And that's equal to our force. Now this term should look a little bit familiar to you guys who've reviewed kinematics lately, because yes, this is our kinematic definition of acceleration. And so we see that our conservation equation for when we have an open system is just going to be following Newton's second law, because this, if we plug this in here, this gives us F equals ma. So that's one of the ways we can remember impulse uses time instead of distance. I know that's a common mistake a lot of my students will make, is they tend to confuse impulse with work. And it's kind of fair, because they play a very similar role in our equations. They're kind of this outside piece for a conservation equation. They both have to do with force. It's really kind of a tricky nuance to keep track of which one's which. So hopefully this is a nice way to kind of derive this if you ever get stuck on the actual test and you don't have any resources that can help you. Cool. So I think with that, oh, and I suppose once again, I will have my chat window up to the left here. So if you see me kind of turning to the side like that, that just means I'm checking to see if you guys are saying anything. If you have any questions about what I'm doing, or you have any questions about the problems, you don't understand what they're asking, just drop me a comment on the chat. I'll try to check these periodically, and we'll yeah, I'll go over anything that any confusion spots. That being said, I think we're ready to see some problems in action here. We've got a little bit more multiple choice than usual, I believe. Yeah. And so we're going to start right off the bat with some car of mass m traveling at a speed v. It stops in time t when the maximum braking force is applied. So this is our signal to us knowing that we're probably going to be using impulse because we have a time for a force. Assuming that the braking force is independent of mass, what time would be required to stop a car of mass 2m traveling at speed v? So if we have the same force, we're changing our momentum down to 0, right? So because we're looking for the case where our final momentum equals 0. Is this within? Okay. I also have to check over here to make sure I'm not going to be writing in a spot that's covered up by something on the screen. But I'll get the hang of that once we get a little ways in here. And our initial momentum is just going to be the mass m times the velocity v. And so we then have 0 is equal to mv plus our impulse, which was that force, which we are saying is going to be the same each time, times our time. And so we can see that our impulse is really equal to negative mv. We're trying to reduce our momentum by a magnitude of mv. And by using this force, we're able to stop in some time t. But now we want to think about what happens when we double the mass. Well, we have to double, if we multiply this by 2, we're increasing this side by 2 also. If we see here, I wish I could move that over, because now, okay, well, I guess I'll multiply by 2 on the outside like that. We realize that this has to double somehow also. And we were told that the braking force is independent of mass. So that tells us that the force will not double, which means this 2 has to apply to the t, giving us a time of 2t. It's going to take us twice as long to stop if our car is twice as heavy. Good. Alrighty, next we're looking at a block of mass big M, initially at rest on a frictionless floor. The block is attached to a massless spring with a spring constant K, initially at its equilibrium position. And then we have an arrow with a mass little m, and velocity v is shot into the block. The arrow sticks into the block. What is the maximum compression of the spring? So we want to start by looking at this as a collision. In the beginning, our block of mass big M is at rest. So the momentum for that is m times 0, which just goes to 0. We're going to run out of space a little bit here. But our moving arrow has a mass and a velocity, so this has an initial momentum. After the collision, though, our blocks will move together because the arrow gets stuck into the block, and then they both keep traveling along. And so this is going to look something like little m plus big M times some new velocity. We'll call this v final. And so now we can solve for this v final in terms of our original velocities. That would be by dividing by big M plus little m. Oh, I'm kind of blocking it. There's a v final up here. That's also blocked by my head. That's okay. We'll put a v final here. There you go. Can you see that? There we go. Okay. So v final times little m plus big M. That's our mass times velocity. I'm going to X that one out. So that means our v final is just going to equal this mv over little m plus big M. And now we want to compare that to the compression of a spring. To do this, we now need to take this velocity and compare it to a change in energy. We have some kinetic energy when once the arrow has hit the block and the block is moving towards the spring, of 1/2 mv squared, where our mass is little m plus big M, and our velocity is this vf squared. And then this is going to equal, at the end, will be all of our energy goes into potential energy, which will be a spring potential. So that's 1/2 kx squared. And so we want to get this x term on its own. This term is the compression, which is what we want to find. So we're going to try solve for that. We're going to divide by, or multiply by 2, divide by 1/2 is the same thing. Divide by k, and then we'll take the square root. So we have, let's see, m plus m times vf squared over k is equal to x squared, but then we'll take the square root of both sides, and we get this option here, although we still need to convert this vf squared into our v that we had before. And so, let's see, that's then going to be, inside the square root, we've got little m plus big M times mv squared over little m plus big M that I just screwed up there. There we go. That's also squared. And then this is all over k. And so we can cancel this with one of those. We get square root of mv squared on the top, and on the bottom we have k times m plus m, all under a square root. So that's going to look something like, once we simplify this, because this was all under a square root, remember, we have the mv just kind of coming out because the square root undoes this square operation on the top. And then these two are both in a denominator, so we can combine these together. And they're still under the square root. So that's going to be k times little m plus big M, which is going to be our option D here. They just put the k on the other side. But k is multiplying this, so that means it can commute. Good, good. Yeah, we're probably going to need to get a second page for this one because I feel like we're going to run out of space very quickly. But that's okay. We'll deal with that when the time arises. Next, we're dealing with two objects, P and Q, and they have the same momentum. Now, Q can have more kinetic energy than P under which circumstances? So if we want to compare momentum, which we know is mass times velocity, to kinetic energy, which is 1/2 mass times velocity, but the v is squared, 1/2 mv squared. So we see that the velocity has a much bigger effect on the kinetic energy than it does on the momentum. So this tells us Q can have more kinetic energy if it has more speed than P. The magnitude of the velocity is higher. If they have the same mass, or a larger mass, that just scales it up at the same rate. Yeah, Q can have, I mean, technically it could have it as the same mass as P, but that's kind of the trivial answer. That wouldn't actually help us because that implies that it has to have more speed though. We technically don't worry too much about the mass because it has the same effect on the momentum as it has on the kinetic energy. So next we've got, oh, no, but we couldn't do that if this had more speed and then equal momentum, because if it had the same mass, then it wouldn't have equal momentum. So B is not true. Just kidding. Sorry about that. But yeah, we're just kind of taking these. You want to analyze each option, make sure that we're not missing anything. So we're going to go through these. As usual, we're going through these a little bit slower than you would on the actual test, just to make sure we're showing each step properly here. 4, we've got a spring is compressed between two objects with unequal masses, little m and big M, and held together. The objects are initially at rest on a horizontal frictionless surface, and then when released, which of the following is true? So when we release these, both are going to push off of each other. Now we expect our net momentum to equal 0, but that's because they will have equal and opposite momentum, scaling to their mass. Because we can think of in the beginning, this is going to equal 0 because they have no velocity together. But afterwards, you can think of this having like one mass is traveling at some velocity in, let's say, in the opposite direction to the second mass, which would then say is traveling in the original direction. So these two are kind of exploding outwards, going in opposite directions. This is a negative term bringing us over, saying that the quantity of the mass times the velocity has to equal the mass times velocity for the other block. So if it's got a larger mass, it's not going to be moving as fast. And so we don't expect the total final kinetic energy to equal 0, because kinetic energy deals with the square of velocity, which doesn't care about direction. Two objects will have equal kinetic energy. That's also not true because we don't expect these to have the same velocity. And their masses are unequal, and this is going to scale. We expect these to have equal momentum, but therefore that means they will have unequal kinetic energy. The speed of one object is equal to the speed of the other. That's not going to be true either. The total final momentum of the two objects is going to be 0. This is going to be true, and this one seems unintuitive, but this is because we expect that positive momentum to cancel out with the negative momentum. Each object individually has non-zero momentum, but the sum of the two should equal 0. Cool. So 5 looks like we're dealing with a numbers problem now. We've got two football players with mass 75 kilograms and 100 kilograms run directly towards each other with speeds 6 meters per second and 8 meters per second respectively. If they grab each other as they collide, the combined speed of the two players after the collision would be which? So let's look before the collision. We have our first mass was 75 kilograms, and he was traveling at 6 meters per second. We'll have his direction be the positive direction. Actually, so he's probably going to get bowled over because he's the smaller guy. The 100-kilogram guy is going faster. I actually take that back. Let's define his direction as the negative direction, because this will then give us a positive answer. And so that then gives us a positive 100 kilograms times our 8 meters per second, which is what our second football player was traveling at. And this, after the fact, will equal their combined masses, because they're grabbing each other, and so they're moving together as one combined mass, which will be their masses summed, so 75 kilograms plus 100 kilograms times their new velocity. We'll call that V final. And so we just want to solve this for V final. And so we've got 100 times 8, so we have a positive 800 kilograms meters per second. And then we have a negative 6 times 75, which 150 times 3 is 450. That is also in kilograms meters per second. I'm probably not going to write that out every time, just because that's going to get a little tedious, but that's okay. And then to get VF on its own, we have to divide by this total mass. And so that's then going to be divided by 175 kilograms, which is the sum of 100 plus 75. Advanced courses, everybody. And so we have 350 divided by 175. I used a calculator for that, but it's just 2. I probably could have worked that out. That's okay. You will get a calculator on the actual test, although you're not allowed to use a cell phone, so make sure you have an actual calculator. I believe you're allowed to have up to a TI Nspire CAS, which is an excellent calculator. We'll talk about this more on the towards our later ones, once we just start discussing like just the AP test strategies and different things we can do for the test. But yeah, we expect our speed to be 2 meters per second, which would be option A. Cool. Number 6, we have a very similar problem here. We have a 5,000 kilogram freight car. It's moving at 4 kilometers per hour and collides and couples, so it's hitting it and grabbing it and kind of moving together again, with an 8,000 kilogram freight car, which is initially at rest. The approximate common final speed of the two cars will be which? We probably should get a new page, but I'm going to see if we can fit this one on the bottom here. So our initial momentum is only going to be the momentum of the moving cart. The 8,000 cart at rest has no initial momentum. And so we will use this because we're looking for options in kilometers per hour. We're not going to translate kilometers per hour into meters per second. Just remember that this will give us a velocity in units of kilometers per hour. But that's fine because that's what we're looking for. So that's kilometers per hour. And then this shall equal our final momentum, which is the sum of the two masses together, traveling at some new velocities together, which would be, we'll call that VF. And so to get VF on its own, we'll just divide both sides by that new mass. Now 4 times 5,000 is 20,000. That's the right amount of zeros. Divided by 5,000 plus 8,000 is 13,000. So that's going to be about that's probably the 1.31. Let's get check on a calculator here. 20,000 divided by 13,000. And the thousands are going to cancel out, so I probably could have just got away with 2 divided by 1.3, but that's okay. And this gives us a final velocity of 1.53, and that's in kilometers per hour. And so our closest option is going to be C, if we round down to the nearest tenth. Good. So I think yeah, I think at this point we do need to get a new page. But that's okay. Well, let's take a look at the problem here, and then we'll, ooh, okay, we're good. Technology is going to be a little bit glitchy, but that's okay. Oh, well, 7 we actually probably don't, because 7 is a graph problem. So we have a rubber ball is held motionless at a height h0 above a hardwood floor and then released, assuming that the collision with the floor is elastic. So this tells us that we expect all of our kinetic energy to be conserved. Which of the following graphs best show the relationship between the total energy of the ball and its height above the surface? Well, this is kind of an energy problem, isn't it? I guess elastic is in collisions, which is kind of part of momentum, but elastic tells us that no kinetic energy is lost. So the total energy, it starts all out as potential energy, falls down, picks up kinetic energy as that potential energy dwindles away, but the total energy is going to be a constant. So this is just going to be option A here. Good. Any questions on that? No? Looks good. You guys are great listeners. Next, for 8, we've got 2 carts are held together. Cart 1 is more massive than cart 2, as they are forced apart by a compressed spring between them. Which of the following will have the same magnitude for both carts? So they're not going to have the same velocity or the same change in velocity, because if they're held together, they'll be starting at the same velocity, and then when this force pushes them outwards, it's going to accelerate them unevenly, scaling by their mass. Once again, we expect these are third law pairs, so the force is what keeps them bound, but then that means their acceleration will be inversely proportional to their mass. The smaller the mass, the more this force can accelerate them. And so in this case, that would be cart 2 gets accelerated faster than cart 1. So cart 2 will have a higher velocity, a higher change in velocity, and also a higher speed. That will not be the same magnitude for any of those, but it will be the same force because these are still a third law pair. The spring is pushing off of each cart equally, equal in opposite directions. Newton's third law. So 9 is where we'll need to get our extra page that I made 2 questions ago that we haven't used yet. So we've got a ball of mass 0.5 at a speed of 6 meters per second, collides with the ball, bounces off with a speed of 4 meters per second in the opposite direction. What was the impulse? So we said the mass was 0.5 kilograms. Is that in a good spot? That's in a good spot. Okay. I kind of like actually the dotted lines. All right, not the dotted lines, the grid lines. I know it's not especially helpful, but it's kind of nice. So our initial velocity, we're going to have towards the wall as being the positive direction. And so this tells us then that our final velocity of the 4 meters per second is in the opposite direction to that, so that's going to be a negative value. And so we can find the magnitude of our impulse as just the change in our momentum, or our P final minus our P initial. And in this case, that would be our mass, 0.5 kilograms, times our final velocity, a negative 4 meters per second, minus our initial velocity, which was a positive 6 meters per second, but we include the negative because we're minusing it, right? That's this minus there. Cool. And that is 0.5 times negative 10. So that is going to be, our impulse magnitude is going to be 5 Newton seconds, or kilogram meters per second if you prefer. And so this is technically in the negative direction, but I believe we were just asked about the magnitude. Yep, there we go. The magnitude of the impulse. So that's going to be B. Awesome. So last one for this page here. We've got a cart with mass 2m, has some velocity v, before it strikes another cart of mass 3m at rest. The 2 carts couple and move off together with what velocity? So we've got, let's have a little picture of what we've got going on here. There's a cart of 2m traveling with some velocity v, and it's going to come and hit this cart 3m until we go to these two moving together, so we can think of this as a cart of mass 5m traveling with some final velocity, which I didn't change the colors for the velocity vector like I had before. I might as well do that, make things a little bit more consistent, easier to learn that way. And so our initial momentum, this object, the 3m cart, is at rest, so it doesn't contribute any momentum to the initial momentum of the system. The initial momentum of the system is just going to be 2mv, the mass of 2m times the velocity v. And this is going to equal the momentum of the final momentum of our system, which is the sum of our two masses, 2m plus 3m, or 5m, times vf. To get vf on its own, we're just going to divide both sides by 5m. So we get it is 2/5 of our initial velocity, which is option B. Cool. Any questions on these so far? Oh, we've got a viewer here. Want to become famous by followers and viewers. I don't think I'm going to do that. I appreciate your offer, but I'd rather try get viewers the old-fashioned way. As best or worst as I can attempt that. But at least we're going to try provide students with free content to help them study for their AP tests, which is what we're all about here. Next, we've got our first multiple correct that we've seen today. So we're going to choose two answers. So consider two laboratory carts of different masses, but identical kinetic energies. They're missing an S there. Let's grab that. Good. Which of the following statements must be correct? The one with the greatest mass has the greatest momentum. No, that's unlikely to be true, because if their kinetic energies are identical but their masses are not, then the velocity is going to be the deciding factor in what makes the lower mass reach the equal level of kinetic energy. Therefore, the smaller mass cart would have the larger momentum. So A is not true. The same impulse was required to accelerate each cart from rest. They have different masses, but identical kinetic energies. I don't think we can assume that's true either. So that means they would have had the same change in momentum. But we expect these to have unequal momentums because they have equal kinetic energies and unequal masses. So B, unfortunately, can't be true either. Both do the same amount of work as they come to a stop. That is going to be true because changing kinetic energy, bringing all of our kinetic energy down to 0 kinetic energy, is going to be the magnitude of the work done. And if these have identical kinetic energies, the magnitude of the work needed to bring them to a stop has to be equal. The same amount of force was required to accelerate each cart from rest. Oh, that's kind of tricky. Yes, because our force is going to be So as we change our masses, they're going to accelerate them differently, but this is going to push them up to the same kinetic energies. They experience so they didn't experience the same impulse, but they can experience the same magnitude of force. Yeah, that is fair. And that's good because we've ruled out A and B also, so this is our best option to choose too. Good. Next we have mass m has some speed v. It then collides with a stationary object of mass 2m. If both objects stick together in a perfectly inelastic collision, what is the final speed of the newly formed object? This is literally the same as the last one we did before, with the 2m and the 3m cart coming together. Only in this case, we have just a cart of 1m traveling at for our initial momentum. The 2m cart is stationary, so it doesn't contribute any initial momentum. And then our final momentum will be the sum of these two. And so to get our final velocity, we'll divide both sides by 3, cancel the m, giving us Vf is equal to 1/3, oops, that shouldn't be a VF, 1/3 of our initial velocity. If anything, that should have a little I for initial, but they describe it as V, so we're just going to leave it as, well, I guess I already changed it, but that's okay. Yeah, and that's going to be option A there. Any questions on how we set that up? Nope, you guys are following along great. Next, we've got a 50-kilogram skater at rest on a frictionless rink throws a 2-kilogram ball, giving the ball a velocity of 10 meters per second. Which statement best describes the skater's subsequent motion? So, if he's standing and he throws the ball, if he starts at rest, the initial velocity, the initial momentum is 0 if he's holding the ball. Then he gives the ball a velocity, so we have our initial momentum is 0. The mass of the ball is going to travel 10 meters per second. So we've now given it a momentum of 20 meters per second. That has to come from somewhere. That comes from the guy. So for his mass of 50 kilograms, he then has to accelerate some velocity, and we're going to see this is going to end up being a negative number. So we can start by bringing this term over to the other side by minusing it. So we'll get a negative 20 kilograms meters per second for the momentum of the ball thrown. And that's going to equal 50 times our velocity that we're looking for, the velocity of the skater. And then we'll divide both sides by 50 to get our velocity is equal to negative 2/5 of a meter per second. 2/5 of a meter is 0.4, and that's going to be in the opposite direction. That's what this negative sign gives us. Good. Any questions on that? Cool. 14, we've got a student initially at rest on a frictionless frozen pond. Okay, so this is the same problem again. Oh, but this is now a qualitative description. So which of the following correctly, while a student moves off in the other direction, the hammer will have the momentum with the greater magnitude. That's not going to be true. The hammer will have the same magnitude. The student will have the momentum with greater magnitude. Also not true. The hammer will have the greater kinetic energy. Now, the hammer is probably going to be traveling at a higher velocity because we can assume the hammer is lighter than the student. Unless you've got a student that weighs less than 1 kilogram, in which case, get him something to eat. And so, hammer has a higher velocity. If they have equal momenta, higher velocity means greater kinetic energy. So C will be our best choice here. The student will have less kinetic energy, so D isn't a good option either. Good. Alrighty then. 15, let's take a look. We've got 2 toy cars with different masses, originally at rest, are pushed apart by a spring between them. Which 2 of the following statements would be true? Both toy cars will acquire equal but opposite momenta. Both toy cars will acquire equal kinetic energies. The more massive toy car will acquire the least speed. The smaller toy car will experience an acceleration of the greatest magnitude. So this is actually a pick 2 one without it saying multiple correct. So they will acquire equal and opposite momenta. If we have something being pushed apart by a string between them, that means they're third law pairs. They're experiencing the same force at the same time, the same impulse. Same impulse means, therefore, we have the same change in momentum. So if they're both starting at rest, going from 0 momentum, rising up to this new momentum, they have to have equal and opposite momentum. Same kinetic energies, different masses. We can't assume that's going to be the same thing. But D is a good option here. The smaller toy car, the one with less mass, will experience a greater acceleration. That is going to be true because they experience the same force, but remember, our acceleration is inversely proportional to mass. So if force remains the same, but our mass gets smaller, the acceleration is going to increase. So D is also going to be true. 16, we've got a tennis ball of mass m rebounds from a racket with the same speed v that it had initially, as shown here. So it kind of comes in, let's see, it comes in the bottom this way and goes up that way. The magnitude of the momentum change of the ball is going to be what? So we're technically, so we're redirecting our velocity, but we're only redirecting the horizontal part. I don't know if you guys can tell here, there's some angle theta. So the horizontal component is being redirected to the magnitude of, if this was just going straight horizontal, it would redirect with a magnitude of 2mv. But now we want the component that is adjacent to this side, relating the adjacent side of a triangle to a theta, to the hypotenuse. That's got to be the cosine relation. So that means D is going to be our best choice. We once again still expect to have that 2mv behavior because we're removing all of that initial momentum and then reincorporating it backwards out there. Mass doesn't change, so we have to change by twice our velocity, but just the x component of our velocity. The y component is still going to be pointing upwards. Good, good. All right, 17. We've got two bodies of masses 5 and 7 kilograms are initially at rest on a horizontal frictionless surface. A light spring is compressed between the two bodies. These are starting to get a little samey. Seems like there's only so many different momentum problems they can ask before they start repeating themselves. We haven't done any two-dimensional momentum. I suppose that might not be on here anymore. That's okay. Two bodies of mass 5 and 7, initially horizontal. Yep. We saw that. After the spring is released, by burning through the thread, the 5 kilogram body has a speed of 0.2 meters per second. Speed of the 7 kilogram body is going to be which? So we expect from the relation that these will have equal and opposite magnitudes. We can bring this around to say that their magnitudes will be the same, like this. And so we know 5 times 0.2 will be our m1. So 5 times 0.2, that's just 1 kilogram meter per second, is equal to 7 times some v2. We want to get this v2, so we'll divide by 7. That's going to be 1 over 7. Look at that. That's 1/7, option B. Cool. Any questions on that? No, you guys are doing great. All right, our last one for this page here, we've got a satellite of mass m is moving in a circular orbit of radius r at a constant speed v around the Earth, which has mass me. Which of the following statements must be true? The net force on the satellite is equal to mv squared over 2 and is directed towards the center of the orbit. That's so close to being true, but it's not, because it would be mv squared over r. Our r isn't 2. Our r is r. So A can't be true, sadly. The net work done on the satellite by gravity in one revolution is 0. That is true. If we remember from our last session, work done in centripetal force ends up being 0 because the force is always going to be perpendicular to the direction of motion and displacement. And so perpendicular, the cosine term goes to 0. So B is going to be true here. The angular momentum of the satellite is constant. That is also true. We expect angular momentum to be conserved. And then D, the net force is equal to gmm over r. Again, so close, but this is not true. The net force would be equal to gmm over r squared. We need to have two r's on the bottom. This would be the potential energy of the satellite. Without the satellite's mass. No, we'd include the satellite's mass. Never mind. Excuse me. But yeah, the force is not equal to the potential energy, unfortunately. But that's okay. Cool. Well, let's move on to the next page here then. I believe this is our last page of multiple choices, and then we can take a look at some FRQs. 19, we've got two pucks are firmly attached by a... Oh, come on. Okay, it's the same type of thing. Oh, no, but it's an initially stretched string and then held at rest on a frictional surface. Then they're released simultaneously. Which of the following quantities is the same for both pucks as the spring pulls the two towards each other? The magnitude of momentum. We've been through this, right? Acceleration isn't going to be the same. Speed isn't going to be the same. Their masses are different. So the changes in masses is going to affect everything. If they have unequal masses but equal momentum, they can't have equal kinetic energy. So that rules out A, B, and C, leaving D as our best option. 20, we have which of the following is true when an object of mass m moving on a horizontal frictionless surface hits and sticks to an object of mass m which is greater than that. So if it hits and sticks, that's not elastic. Elastic we expect to be kind of bouncing off. When it hits and sticks, this would be called an inelastic collision. I'll write that down here. Inelastic. The momentum of the objects that are stuck together has a smaller magnitude than the initial momentum of the less massive object. It's close, but that's not true. We still expect momentum to be conserved. What will be smaller is the velocity. Speed of the object. Oh, so that's option C. Look at this. The speed of the objects that are stuck together will be less than the initial speed of the less massive object. That will be true, because we have to have the same momentum, but now we're moving a much larger mass, which is the combined mass of the little mass and the large one. The direction of the motion of the objects that are stuck together depends on whether the hit is a head-on collision. Kind of? Not really. I mean, it vaguely depends on how it hits it, but it doesn't depend on whether or not it is a head-on collision. That's kind of then implies the orientation of M, of big M, which really shouldn't matter. We expect the direction that the little mass hits big M to be the same direction that the two masses will continue going. 21, we have two objects having the same mass travel towards each other on a flat surface, each with a speed of 1 meter per second relative to the surface. Same mass, same speed, so they have the same initial momentum. The objects collide head-on and are reported to rebound after the collision, each with a speed of 2 meters per second relative to the surface. Which of the following assessments of this report is most accurate? Momentum was not conserved, therefore the report is false. It's tempting, but that could just mean there was an outside force. If potential energy was released to the objects during the collision, the report could be true. That would be a case. If we hit a spring, then that would be releasing potential energy. That's applying a force. If the objects had different masses, the report could be true. No, that doesn't really help us. If the surface was inclined, the force could be true. Not really. Yeah, because that would just be a slow acceleration. They wouldn't have a rebound change. If a potential energy was released, though, this could work. So that, like, most likely would be a spring bouncing off of it. It's applying a force to accelerate, but releasing potential energy is the same thing as that force doing work. Yeah, I think we discussed that last time. 22, a solid metal ball and a hollow plastic ball of the same external radius are released from rest in a large vacuum chamber. When each has fallen, they both have the same which. So we're assuming their mass is not the same. So if their mass is not the same, they would not have the same momentum. They would not have the same change in potential energy because the one with a larger mass will have lost more potential energy. They would still, if they're traveling the same distance, they would have accelerated the same amount, so they would have the same speed. In fact, this was an experiment done in 1969 on the moon. We had, I believe it was Buzz Aldrin, had the hammer and the feather, and he dropped both in a vacuum because the moon has no atmosphere, and they both fell at the same rate, which normally we would not expect to happen, because on Earth, a feather is going to get caught in the air and slowed down, but an object accelerating just due to gravity will fall at the same rate. Cool. Yeah, it's a pretty neat video. I'm sure you can find it on YouTube somewhere. If you're already on here, watching this grumpy face, you might as well look up a little piece of history there. It's worth your time. 23, we've got a railroad car of mass m is moving at a speed v when it collides with a second railroad car of mass big M, which is at rest. The Cars lock together and instantaneously move along the track. What is the kinetic energy of the cars immediately after the collision? Okay, so that's kind of a nice change of pace, I suppose. Now it collides and locks together. This is an inelastic collision, which tells us that we don't expect kinetic energy to be conserved. So we can't just go from 1/2 mv squared to 1/2 big mv squared like that. We can't do that. That it only works for elastic conditions. But what we can do is we can use our inelastic momentum conservation and then plug in the velocity we would find into our kinetic energy. And so we have initially just a mass of m traveling at some velocity v, and then afterwards we have the combined mass, so little m plus big M, traveling at some v final. So v final will equal little mv over little m plus big M, and we can plug this in to our kinetic energy. We expect this to be of the form 1/2 mv squared, but our m is going to be this combined mass, and our v is going to be this vf squared. So that's going to be our mv over m plus m squared. And if we like, we can cancel out one of these with one of the m's down here. Now bear in mind this is squared, so this is really, excuse me, this is really still just going to be, we'll have an mv squared on the top, and then the 2 from the 1/2 on the bottom, and we still have one more of the little m plus big M. But this term is no longer squared. Is that one of our options we're given? Oh, one of our options we're given is the unsimplified version. That was just this level here. Oh, I gotta stop doing that. I want to start using these better. The laser pointers are just so cool. Alrighty. Cool. This looks like our last multiple choice here. We've got an open cart on a level surface is rolling without frictional loss through a vertical downpour of rain. Oh, this is interesting. Actually, kind of a change. So as we keep going, an appreciable amount of the rainwater accumulates in the cart. This is going to raise the mass of the cart. The speed of the cart will decrease due to conservation of momentum. So what we have happening is if we have no frictional loss, so we expect our momentum to be conserved, we initially have some m and some v. As our m gets larger, our v has to decrease, and our m is getting larger because we're adding water. So our velocity, or speed, the magnitude of our velocity, is going to decrease due to conservation of momentum. Cool. And so, yeah, I believe that is all we have for our multiple choice today. I'm going to grab a quick drink of water here, and then we're going to take a look at these FRQs. You can take a look now if you want to get ahead of us. How are we doing? Not a lot of activity in the chat, but I assume that's just because you guys are all understanding everything that I'm saying perfectly. I'm sure that's a fair assumption, huh? Okay. So, we've got a question from 1990. Got a bullet of mass m is flying at a block with some initial speed v0, and it hits a block of mass 100m, weighs 100 times as much as this bullet, on a horizontal frictionless table. The surface of the table is a height h above the floor, and after the impact, the bullet and block slide off the table and hit the floor a distance x from the edge of the table. So we can kind of see it follows this nice little trajectory and then falls down. Derive the expressions for the following quantities in terms of m, h, and v0, and appropriate constants, which probably is just going to be g. So we want to find the speed of the block as it leaves the table. So the speed of the block after it leaves the table, we're told this table is frictionless. So this is going to be the same speed as after the collision. And this is going to be just like our inelastic collision problems. We start with only the bullet contributing some initial momentum. the mass of 100m is sitting at rest, so it's not going to be contributing any momentum before the collision. But after the collision, we have the two masses, m plus 100m, is going to be traveling at some v final. Getting that v final on its own is going to equal our m v naught divided by 1m plus 100m is 101m, which we can divide by m just to get, in terms of v naught, our v final is equal to v naught. It's 1/101st. Oh, I don't know how you'd pronounce that fraction, actually. It's like 1/100th, but plus 1. 101st. I'm sure that's not how you pronounce it. 101th. Oh, that's worse. Well, yeah, but this is going to be our velocity. This small fraction of our initial velocity. And that makes sense, because bullets travel very quickly. The change in kinetic energy of the bullet block system during the impact. So that's just going to be our initial kinetic energy minus our final, our final kinetic energy minus our initial kinetic energy. Is this covered by my face? A little bit, not too bad. Our final kinetic energy is going to be this 1/2. Our mass is 101m, and our VF is V naught over 101, and we're going to square that. And then we're going to minus from this a 1/2 times our initial kinetic energy, which was just the kinetic energy of the bullet. Remember how our block was not moving. So this is just of m times v naught squared. Let's see. And so the 101 squared cancels with one of these 101s, giving us a loss in kinetic energy. So we then have, how do we want to write this? So we'll cancel the 101, and so we'll have this as 1 over, oh, let's put that with the 2, actually. So our 1/2, we still have the 101 from one of the v naught over 101 squared. Top one was canceled. We still have the m, and then we still have the v naught squared, because we didn't cancel that. Ooh. Can I just, like, get a nice dividing line there? Because that's a little bit, little too close, little confusing. And then we're going to minus our initial, which was just this 1/2 mv naught squared. And so this is going to then take us to a negative. So we'll probably want to then treat this as, in the negative realm, 1/2 minus 1/202nd, which I am going to need a calculator for. I'm not that good with fractions. I'm pretty good with them, but not quite that good. Oh, well, I mean, I guess we could just do, so that would be 1, okay, yeah. No, we can do this. We can do this without a calculator. So we can rewrite this as 101/202. And we're minusing this from 1/202, and then this still has the same units. So this gives us a change in 100/202 and v naught squared. This is our delta k, which I guess we can put over here. Delta k, and we can reduce this if we want. I kind of don't want to. I guess we'll do it. We'll do a little bit. We'll do 50/101 times mv naught squared. Bear in mind, I say this every time, but it's worth repeating. You are not required to reduce your answers unless it specifically asks you to. You don't need to simplify, and if you make a mistake while simplifying, you can be penalized for that. So it's usually not worth it. That being said, that was a pretty easy one. We're just dividing it by 2. The distance x. Oh, x as in the distance we flew. Gotcha. So this distance x is going to be, we can think of this as our final velocity, like, because that was our velocity we have in the x direction, times the time that we were in the air. Which, plugging in terms of things we have, is v naught times t over 101. But now we need to solve for this time. Get the time in terms of m, h, v naught, and appropriate constants, which is going to be g. And so that's going to be, we have to then use the y equation to work out how long it took us to accelerate down and travel through this distance h. And so the distance in the y that we traveled was h, and that traveled 1/2 gt squared. Yeah, let's put that as an h. And so to solve for t, multiply by 2, divide by g, and take the square root, giving us t is equal to the square root of 2h over g. Good, and that's in terms of the constants we have. We can plug that in for our x, giving us an x value of v naught over 101 times the square root of 2h over g. Can we fit that up here? I think we can fit that up here. Good, good. And this is our x. Very nice. So now we're looking at the case where we suppose the bullet passes through the block instead of remaining in it. State where the time required for the block to reach the floor from the edge of the table would now be greater, less, or the same. So the time to reach the floor is actually not going to change. This was only determined by this. If we look at our equation down here, we see the time only depends on the height, which we're assuming isn't changing, and acceleration due to gravity, which we're also assuming isn't changing. We could think about the force is going to change because technically the block is going to have a little less mass now, but the acceleration due to that force is not going to change. That is invariant. So we expect this to be the same. And I just justified my answer verbally, so I'm not going to write it all out. But now we have to then consider whether the distance for the block would now be, distance x for the block would now be greater, less, or the same. And so this does depend on this v final term here. See how this has the v naught over 101? That was this v final. Now the v final is going to change if the bullet goes through the block. If the bullet goes through the block, that means it's coming out on the other side. And so that means that after it finishes, it's going to continue traveling at some velocity. Now, presumably, this will be less than v naught because it will have imparted some energy into the block, but it's going to be greater than the velocity of this block because otherwise it wouldn't have passed through. If it was less than that, it would have stayed stuck in it. So that means that this VF is going to be less than, I guess let's call it, sorry, VF prime, like the new one, is going to be less than our old one. And so if this gets smaller, our distance x will now be less because VF prime is less than VF. Does that make sense qualitatively? Why we expect this to go down? Because of the bullet coming through? Okay, well, it looks like we have no questions on that. Mathematically, we can show it that way, but it's kind of a pain. And we're not asked to show any mathematics here. We just want to defend our answer, which I think I did verbally. Cool. So if there's no questions on this FRQ, I'm going to move on to the next one. So next, looks like kind of a short one here. We've got a block of 2m coming up to hit a block of mass m that's on the end of a spring here. I guess x naught is the resting spring. Yep, it's x naught is our relaxed distance, and it has some spring constant k. So we want to find, we want to start with the velocity of the two blocks after the collision. This is probably easier than what we would see an actual FRQ to be. This is kind of, this is then just going to be 2m v naught So the only thing contributing momentum at the beginning is going to equal the combined mass, so 2m plus 3m, sorry, 2m plus 1m, which equals 3m, that's why I had that on the mind there, times some new velocity that we want to find. And so that v final is just going to equal 2m v naught over 3m. We can leave it like that. We can cancel the m's out, which, again, not hard to do, but technically you don't want to be playing too risky, but that's fine. This is a pretty simple one. Yeah, so we expect our final velocity after this impact to be 2/3 of our initial velocity. Yeah, I think literally both of these parts were single multiple choice earlier, because now we want to find x, the maximum distance the spring is compressed. And so that would be us translating from a kinetic energy with a mass of 3m and a velocity of vf squared into a spring constant, a spring potential energy, which would be the maximum distance. We want to get this x on its own, so we'll multiply both sides by 2, divide both sides by k, and take the square root. So we get x is equal to 3m over k times vf squared, all under the square root. And we want to plug in vf. So this is going to equal 3m over k times 2/3 v naught squared. That can reduce a little bit. The 3 can go away, and then we get a 4 up top. I don't really want to do that. I don't really care. It's this is a really short problem that is, yeah, kind of underwhelming, to be honest, for an FRQ. But that's fine. Hopefully we can find something a little bit juicier for this last one. Oh yeah, this is what I'm talking about. So we've got a nice loop-de-loop action going on here. We've got some small block of mass 2m is initially at rest on a track at the bottom of a circular vertical loop-the-loop, which has some radius r. The surface contact between the block and the loop is frictionless. Okay, so we're not going to be dealing with friction, so we can expect all our conservation rules to apply. The surface no, I just read that. A bullet of mass m strikes the block horizontally with initial speed v naught and remains embedded in the block as the block and bullets circle the loop. So we want to now determine these all in terms of m, v naught, r, and g. Speed of the block and the bullet immediately after the impact. Okay, we've done this a lot now, but it's worth going over again. mv naught, only piece contributing momentum in the initial scenario. Excuse me. And then afterwards, we have a combined mass of 2m plus 3m. It's literally the same scenario. And some velocity there. So our VF is, once again, 2/3 of our V initial. Cool. Then the kinetic energy, which is going to be 1/2 times our new mass, which is 3m, times our velocity squared, which is that 2/3 v naught squared. And in this one, do I want to? No, I'm going to leave it like that. This is our kinetic energy. We can leave it like this. I say if we're going to use this later, this might help to simplify it because it might make a later problem easier, but not going to bother with it. How we doing on time? We're looking pretty good, actually. And so then for C, now we have to find out what is the minimum velocity that we need for the block at the top of the loop such that the loop remains in contact, that we remain in contact with the loop at all times. So the condition for this would be we want our normal force to be greater than 0. So at the limit, that's going to be at when our normal force is equal to 0. It's the lowest velocity we can go. Or technically we want to go just slightly above it. But that's going to be our limiting case here. And that is going to show up from centripetal force. So our centripetal force is going to be the sum of our forces pointing radially inwards. And at the top here, we have two forces pointing radially inwards. We have the normal force from the from the surface of the loop, and the gravity force. And so we'll label these as Fn and Fg. And so we expect the sum of these two, Fn plus Fg, to equal our centripetal force, which we define as mv squared over r. But bear in mind, this is with the bullet and block combo, so we're going to use 3m for our mass. So we have 3m v squared, this is that v min we want, over r, which is just r. That's convenient. And so we want the case where Fn goes to 0. And so we want to solve for v min, where this goes to 3mg. So let's see, we have 3mg is equal to 3m times v min squared over r. We can divide both sides by 3m. And so we get the v min, if we multiply both sides by r and take the square root, is equal to the square root of g times r. So invariant of the mass, which is good to know. And so this is the minimum velocity we have to maintain at all times. So now we need to find what is the required entry speed of the bullet and block combo at the bottom of the loop, such that the conditions in part C apply. So we want to make sure that we reach some velocity of v min at the top there. And so to do this, we'll use conservation of energy. At the top, we have a potential energy of 3 mgh, where our h is 2r. And we'll also have a kinetic energy 1/2 times 3m v squared, and that's that v min. So we're going to write this as square root of gr squared, which is just gr. Cool. And then this has to equal our initial kinetic energy, which is the kinetic energy at the bottom, which we'll call 1/2 again with the 3m. But now this is going to be they write this as a v naught prime squared. So that's going to be the velocity we're looking for. And so we can clean this up on top here and kind of combine some stuff. We've got 6 mgr plus 1/2 times 3 is 1.5. Oh, not 1/2. Oh, there's a little dog barking. If only he could be a little quieter. That's okay. We're actually almost done here. And then I'll go play with him. All right. So we have on the left side is just going to be 7.5 mgr. We can cancel our m's, and we want to solve for v naught, so we'll multiply by 2, giving us 15 gr is equal to v naught squared with a prime, and then we'll take the square root of both sides to get v naught on its own. So we need, when the bullet and block start moving together, they need to be traveling at a speed v naught prime of square root of 15 times the acceleration due to gravity times the radius of the loop. Cool. And so now that then tells us what is going to be the new initial speed, of the bullet to produce the speed from part D. So we now want to make sure that this final velocity after our collision is going to be this v naught prime. Now remember, we still had the same setup as this guy. The only difference is we're now invoking a definition on our v final. Our v final has to equal this v naught prime. And we're looking now for this new v initial. This is what we're looking for, this v here. This is, again, the only contributor of momentum at the beginning is from the moving object. This is the speed of the bullet of mass m. And then afterwards, they're going to travel 3m at some velocity, root 15 gr. We can divide by m, and that gives us our vi. Our vi is going to equal 3 times root 15 of gr. That looks like that reduces, but I'm not going to bother with it. Yeah, and that's going to be the initial speed the bullet needs to achieve. Cool. Any questions on any of this? You guys have been doing great. So I actually believe that that was the last one. Thank you for anyone if you watched from the beginning. Yeah, so thanks for stopping by, everybody. Next week we'll be doing, well, this coming week we'll be looking at simple harmonic motion. This is going to be the second to last new chapter. We've almost covered every unit that's going to be on this year's AP Physics 1 test. We will have, after that, will be torque and rotational motion, and then we've only got one more before the test, and that's the last unit, is torque and rotational. Our last session, where we're going to do this kind of live stream format, we're just going to be going over everything. We're just going to look at all the different things, how to identify different problems, what approaches you'll want to use, and then we'll just talk shop about the test itself and different test taking strategies. Once again, feel free to jump in the chat. We can make this more of a discussion. If you guys have any specific trouble spots you want to spend a little bit more time on, we can focus on that. Follow us on Instagram. We've got an Instagram at 3 and 4 Education. This is where we keep information posted about upcoming streams and that kind of stuff. We're hoping to get a little bit more exciting content on there. I mean, right now it's just me running the entire company, and I spend most of my time tutoring. But I want to get you guys content that gets you excited about science, about physics. I want to see what are you guys into? What makes this fun for you? And then, as always, you can check us out at our website, 3 and 4 Education. You can use that to book online tutoring. We can do this remotely, or if you are in the Phoenix area, we could do in-person sessions depending on availability. And I have a couple other fun things going on the website too. We've got a nice little problem blog. We're looking to add new content with some practice problems. Yeah, lots of fun updates to be coming in the future there. Cool. Well, thank you everybody for coming by, and until the next time, you take care, you keep safe. I'll see you guys on Wednesday. Take care now. See ya. Oh, I'm still streaming. Okay, there's the right button.